I'm Carola Schönlieb, I'm Professor of Applied Mathematics. Welcome to my exp. Mathematical imaging, mathematical image processing has been hit tremendously by the emergence and success of deep learning. And so this is really when machine learning has become an extremely powerful tool all of a sudden for image processing. Before we had machine learning, but more low-level machine learning and image processing, but it was not really something that was overshadowing everything else, right? All of a sudden, deep learning happened, and the work that mathematical imaging people have done before, which was mainly based on model-driven approaches, so approaches that are based on mathematical equations, deriving these equations from first principles of understanding what the image is all about, what the problem with this image is, like for instance for denoising or deconvolution, modeling this, and then thinking about how to turn this into a mathematical model that is well posed, that gives you a solution that is robust, that is generalizable, and so on and so forth. All of a sudden, deep neural networks came around where what you throw onto the problem is just loads of data, loads of imaging data that you train these models, these highly overparameterized models with, and all of a sudden they outperform everything else that we have done before. The key insight here is maybe to think a little bit about, in addition to really impressive results that neural networks can do, what the limitations are. And I always like to think about this by putting the two side by side. So deep learning can give you really accurate, very impressive results in detection in images, segmentation, also in image denoising, and so on and so forth. But usually what you train it with is what you get as a result, right? So if, let's say, you only train it on images of cats, it will also only work on images for cats. If you apply it then to an image that shows a dog, if it's a denoising process, in addition to denoising, it might also turn your dog slightly into a kind of cattish dog. These are the things that happen. So it will depend on what you train it with. Which is very contrasted to the traditional kind of principled mathematical equations type of approaches, which are universal. They don't need to be trained. They work in every kind of setting, right? If you apply them to a medical image, they work the same way as they do on an astronomy image, or an image of an art piece. And so they also work in the same way on cats and dogs. Now, they're not as accurate as these deep learning approaches, but this is the natural kind of bias variance trade-off. If you want the accuracy versus robustness, accuracy versus generalizability, universality trade-off that you have. Deep neural networks are mostly a black box. And still, having also worked myself on mathematical foundations of neural networks for many years now, we are very far from what we can explain mathematically, which is for more simplistic neural network approaches, to what is actually used. So it's the explainability, which again, with mathematical equations, we have a lot of explainability and again, trustworthiness. We know with neural networks, things can also go wrong, and the problem is we don't know when they go wrong, because we can't explain it. The exciting thing is to bring them together. This is where the field of mathematical imaging as a whole is moving into more and more, is to put together the best from both worlds, to get the accuracy from neural networks and the tremendous capability that neural networks have to characterize information content in imaging data, together with the principled way of mathematical equations-driven approaches, explainability and so on, and maybe also looking at this from the point of view of medical and scientific imaging, bring these type of approaches to settings where maybe we don't have so much training data available, like in scientific imaging, for instance, where often we use imaging as a tool to explore things we have never seen before. So we can't afford to train on cats and then just see cats in these images because we don't know whether there are cats there or not, if that makes sense. So I think this is where this hybrid methodology between partial differential equations, let's say, to take them as an example of these more mathematical equations-driven approaches, and the deep learning approaches is really exciting. This is where I think the main excitement lies now for me and for many other of my colleagues in the field. Before deep learning came in, we tried to model this prior information in terms of mathematical equations, right? So what are the characteristic features in these abdominal scans? What is really important? The most famous prior assumption that people have been using in medical imaging before deep learning is what is called total variation regularization. That basically says most important information in an image is where organs meet other organs, where there are boundaries between different objects, edges in an image. This is what we really want to preserve, and this is very important if we want to quantify things like segment tumors in images later. But it's simplistic, right? And this is where deep learning, where you know, learning as a tool, making this prior information more data-driven based on a lot of abdominal scans you have looked at in the past, makes it so powerful and makes it more precise. So one of these images, the first one is the ground truth. That is a perfect computed tomography scan with, let's say, perfect measurements. And the other three are scans with lower radiation, with radiating the patient less, which means you get less good data. If you look at the last one, which is the data-driven one, it looks the the closest to the ground truth, because it gets the even with the worst measurements, but drawing connection to a lot of other abdominal scans, it gets really a lot of accuracy, a lot of fine details out of the images. There are scenarios and there are settings where, in particular, pure deep learning approaches can go wrong. In particular, if we are in settings where we rely too much on this highly accurate prior information. In settings where the data is very, very limited, where we have a really much less data that we would need to reconstruct an image from it confidently. And so one technique that comes to mind, in particular used in the biomedical domain, is limited angle tomography. You have a whole viewpoint of the object you're looking at that you haven't measured. And so in these settings where you have huge gaps, like in the inpainting example, like when we think about image inpainting for images, restoration of images, if we think of this in the transform in the medical domain, if we have large gaps in the data, this is where deep learning can go wrong if it takes too much of the prior information into account and doesn't respect the information content in the data. So it might make up things that are not there, right? If you look at this example that we have in the bottom left image and compare that with the ground truth, you see that it has totally made up things like bones that shouldn't be there. The whole shape of the body is different, right? So this is where you see cats where there are no cats, basically. In the context of imaging in particular, I think the main way forward and the main area where mathematical imaging people are at the moment influencing the field is in, on the one hand, structure preserving deep learning, so imposing constraints on neural networks that might come in terms of equations, that might come in terms of symmetries of the solutions that you expect. So some constraints that help you to impose certain properties of the solution that you know the solution should have. or that help you to impose adversarial stability, right? Make the deep learning process more robust. So this is one direction. The other direction is to use deep learning as a plug-and-play tool in the more robust mathematical equations approaches that we have, in a way to enhance these and embed deep learning into a framework that we understand, that is explainable, and that we know is robust.